Hi, if you are still here, you may want to see how I built this engine. In this part of the video, I will show the build process, talk about the problems I had, and ask one question I still don't have an answer to. Let's go! The crankshaft is made from tempered chromium molybdenum steel. Because I cannot make split connecting rods, I decided to make a split crankshaft and assemble it using press fits. To drill the holes symmetrically, I use a special fixture. I press the crank pins into the center crank web. I will make the connecting rods from aluminum. I need a very accurate fit on the crank pins and on the piston pins. The crank pin diameter is about 4 mm. The piston pin diameter is 3 mm. I don't have reamers for precise holes, so I bore them with the boring tool. I think the clearance should be no more than 2 or 3 hundredths of a millimeter. I cut the plate, then split it in half and turn it slightly. I remove extra material with the file. This is how the connecting rods look. The small holes in the rod heads are made for the lubrication. You know what? Instead of filing parts by hand, I could have ordered the connecting rods from GLC CNC. GLC CNC offers a wide range of services: milling, turning, EDM machining, sheet metal, and 3D printing. They work with aluminum, steel, and many other materials. The ordering process is simple and fully online. Just upload your CAD file, select the material, choose the machining options, and place your order in a few clicks. GLC CNC can make parts in as fast as 3 days, with delivery about 5 to 7 days. If you need precise parts for your engineering projects, GLC CNC is a good choice. I install the connecting rod and press in the first crank pin. I try to keep everything as straight as possible to make future work easier. The press fit of the crank pin in the crank web is about 2 hundredths of a millimeter, but I'm not fully sure. It's quite difficult to measure the inside diameter of such small holes very accurately. I install the second connecting rod, align the rear crankshaft journal, and press it in. This is the crankshaft I get. Of course, it is not straight yet, and it must be aligned. Here you can see how crooked the crankshaft really is. The runout is about 0.3 of a millimeter. I mark the spots where I need to bend the shaft so I don't get confused. I use the lever to move the crank pins and reduce the runout. The press speed of the crank pins can shift slightly, which helps to align the crankshaft quite accurately. This is the result I got. The maximum runout of the crankshaft is about 2 hundredths of a millimeter. I think this will be enough. Now I will make the pistons. I have already bored the blank inside. I used cyanoacrylate glue to fix the blank on the shaft. I used the aluminum for the pistons, and later I realized that it was a mistake. Can you guess why? Here is a hint: the cylinder liner will be steel. Remember, the piston diameter is only 14 mm. Pause the video and write a comment now. Later in the video we will see the correct answer. Each piston was fitted to its own cylinder liner. How I made the cylinder liners we will see a bit later. Now we will install the pistons on the connecting rods. Off camera, I have already bored the hole for the piston pin. The piston pin rotates freely on the rod. The press fit of the pin is in the piston itself. By the way, this also turned out to be a mistake. Nevertheless, at this stage, both pistons are installed and there is no turning back. It looks like a beautiful little toy. Let's go back to assembling the engine. I installed the front bearing. Here I use bearings size 8 by 16 by 5 mm. I installed the oil seal. In two-stroke engine, the mixture is compressed in the crankcase, so the seal is necessary to prevent leaks. I put the crankshaft into the engine case. I screw in the bolts, but I don't fully tighten them. The engine case is quite complex. It consists of 2 halves. Let's see how I made it. 2 pieces of aluminum are prepared. They are fitted to each other very precisely. I glue the parts together using cyanoacrylate glue. Holes are drilled for the transfer ports and for the cylinders to create reference surfaces for later reinstalling the part in the chuck. I also make holes for the screw heads. The crankcase halves are fixed with them 2 screws. The crankcase is set in the lathe chuck, and the hole for the crankshaft is bored to a diameter of 19 mm. The holes for cylinder liners are also bored. I installed the rear crankshaft bearing into rear engine cover. The cover is quite simple, so the machining process is skipped. I installed the rear engine cover. The mounting screws are lightly tightened first. This small tightening force pulls the cover against the crankcase, but still allows the crankcase halves to come together when their screws are tightened. Next, the screws of crankcase halves are fully tightened. Finally, the rear cover screws are tightened to their final torque. I installed the cylinder liners. They are made from the same chromium molybdenum steel as the crankshaft. Because the surface after cutting is quite rough, the liners were lapped using adjustable brass lap and abrasive paste. The process of making transfer ports in the liners was not recorded. The inner surface turned out quite smooth, with no scratches or tool marks. I installed the cylinders. They are fixed to the crankcase with 4 M2.5 screws. The cylinders are also made from aluminum. To save time, the cooling fins are turned on both cylinders at once, in a single setup in the chuck. After that, a bit of sanding and polishing is done. The blanks are then cut in two separate parts. The holes for the future transfer ports were drilled earlier. I bored the hole for the cylinder liner. This is how the cylinders look. Here you can also see the transfer ports. The exhaust fittings are installed on M6 threads and glued with epoxy. The cylinder heads are installed next. They are also quite simple to make, therefore the process of making them is skipped. The cylinder heads are fixed within 3 screws. The engine compression ratio is 12. Unfortunately, the process of making the carburetor was not recorded, so I will just show it. Its size is 11 by 11 by 7 mm. It has a cylindrical throttle valve. The throttle bore diameter is 3.5 mm. The carburetor also has a jet needle to adjust the fuel mixture. The fuel jet diameter is 0.5 mm. Here is the process of drilling the fuel jet. The outer diameter of the jet is 1 mm. A 0.5 mm drill is used. It was quite stressful to drill it 5 mm deep. And no, I did not have a tube of this size, so it had to be made from a 10 mm brass rod. The carburetor is fixed with 2 M2 screws. Let's take another look at how the throttle valve works. It also has end stop limits and fuel fitting. I'm installing the exhaust pipe clamps. They are fitting tightly around the pipes. Now I'm installing the Cooper exhaust pipes. Do you think their diameter is small enough to stop engine from starting? And of course, I'm installing the spark plugs. This is how the engine looks now. What next? The short answer is nothing. But still, let's try to start the engine. As fuel, I'm using regular gasoline, mixed it with oil for garden equipment. You can see a very large flywheel and no exhaust pipes. This is because they are not the first start attempts. I just want to show that the engine does not run. The ignition timing was checked, a large flywheel was tested, the valve timing angles were also checked, but none of this worked. Then I accidentally discovered that some of the ignition sparks were jumping in the wrong place. So I decided to buy a proper CDI ignition system for a model aircraft. The engine started to show weak firing, but it still did not start. After the engine heats up, scratches appear on the pistons and on the cylinder liners. This is the answer to why using aluminum was a mistake. It's well known that aluminum expands more than steel when it gets hot. I thought that a clearance of a few hundredths of a millimeter between the piston and the liner would be enough to prevent problems from heat. But there is one more issue. Because the piston pin is press-fitted into the piston deforms slightly. As a result, the clearance becomes smaller in some areas. This leads to contact between the piston and the liner when the engine heats up. I also decided to use a free-fit piston pin with retaining clips. and I decided to increase the cross-section of the transfer ports. And once again, with no result, I decided to switch the engine into nitro fuel and glow plugs, just like in RC nitro engines, and everything changed completely. While trying to make the engine run, the exhaust pipes were removed, and the exhaust ports in cylinders were enlarged. Now, when it is clear that the engine is working, the exhaust pipes will made again. I think the engine looks and sounds better than them. I also decided to add a muffler to the exhaust pipes. Now the sound will be even better. If you know why small engines don't run well on gasoline, please write your answer in the comments. Thanks for watching. See you soon!